Okay, welcome to the last Astrophysics of the year. And today we close with Nianyi, new member. Before joining DIS, she completed her PhD at Carnegie Mellon. She's broadly interested in the use of numerical simulations in astrophysics at different scales, like galaxy formation, supermassive black hole binaries. And today she will tell us about what happens when black holes are not fixed at the center of their host galaxies, but instead they move around. Go ahead.
Hi everyone, I'm Nianyi, as you know. As Jamie said, I will today I will tell you about the modeling of massive black holes in cosmological and galaxy formation simulations, and specifically the modeling of their dynamics and what happens when they are allowed to move around. So here is a brief outline of what I will be talking about. So first, I will give a brief general introduction of the modeling of massive black holes in cosmological simulations, since not a lot of people work on cosmological simulation here. And then I'll focus specifically on the black hole dynamics, and I'll talk about why we should care about correctly modeling them in the simulations and how it is currently modeled and the current progress in the field. And then I'll talk about two main things related to the dynamics of massive black holes. The first one is the seed black hole mergers, because that's a promising probe to the massive black hole seeding mechanism. And then I will also talk about the off-center AGN and massive black hole population we see in the simulations. So a brief introduction on cosmological simulations. So this is like an example of the different scales that we can model and resolve in a large volume cosmological simulation. So this is the simulation that my group had worked on during my PhD, is the Astrid simulation, and it currently reached redshift 0. So it's a full redshift simulation. It has a box size of 250 megaparsecs, so it's one of the largest cosmological simulation to date. And then, so here you can see that we evolve everything from cosmological initial conditions. So we have the large scale structure on the background. And then we also resolve the galaxy groups and clusters and individual galaxies. And within the galaxy, we can also resolve the black hole and star formation down to the resolution limit to about a few hundred parsec or KPC scales. And so in these simulations, we have all the subgrid galaxy formation, stellar physics to treat star formation, AGN accretion, and feedback. And so, for example, we have star formation with supernova feedback. We have different heating and cooling mechanisms, and we also implement the inhomogeneous reionization in this simulation. So today I will specifically focus on the massive black hole and AGN aspect of the simulation. So when you model massive black holes, you model them as sync particles in these simulations. And as a sync particle, what they can do is they can accrete gas, and then they radiate photons, and they also have outflows in different modes depending on the accretion efficiency. And so in this simulation specifically, we have Eddington limited boundary accretion. We have both the quasar and the radio mode AGN feedback. So a specific advancement in the simulation compared to previous simulations, such as the TNG or the Eagle suite of simulation, is we have the dynamical friction treatment to the black holes from both dark matter, star, and gas. And finally, we also model is the stochastic massive black hole seeding motivated by the small scale seeding experiments.
All of the differences between the black hole, like between simulations, is more so in the black hole.
It is, and so in the galaxy formation physics, there are more minor differences. So the star formation model is similar, and also supernova winds. And I think for the for example, for the realization, I think the TNG used a fixed uniform UV background. So we have more of a inhomogeneous realization. And yeah, so the stellar physics are not so different. Maybe we use a different supernova wind model, but they are qualitatively similar.
You mentioned that like with the same particles, the black hole is absorbing a lot of the gas. You also mentioned that you have to treat like the photon flux, I guess, kind of carefully. How is this done in the simulation? Because presumably you're not doing radiative transfer rates. So.
Yeah, no, so we don't so we don't really trace the radiation. So we more have these like we try to model in separate fashion the radiative heating. So the heating to the surrounding gas by the AGN. So basically all the accretion feedback are modeled in a separate fashion. So when we have the Bondi accretion, we just try to estimate the surrounding gas density and the gas temperature and the fraction of cold gas compared to the hot gas. And then that determines the rate at which the black hole accrete things. And then we assume some radiative efficiency, typically 0.1-ish. And then we calculate how much energy is dumped to thermally to the surrounding gas. And then the difference between the quasar and radio mode is mainly that the quasar mode are in this high accretion regime. And it's more like radiative feedback. And then for the radio mode, it's more of a kinetic of feedback, trying to model more of an outflow scenario. So it's more of a kinetic energy dump to the surrounding gas.
How do you decide which one dominates, whether it's thermal or kinetic?
So we have yeah, there's a threshold both in the black hole mass and in the depending on the Eddington ratio. So yeah, there's a switch. I think it happens roughly around 10 to the 9 solar masses and 0.005-ish Eddington ratio. Yeah, there's a scaling, which I don't remember on top of my head, but there's a roughly on that regime. In that regime, we switch to the kinetic
So
mode.
is that motivated by small scale simulations of accretion, background accretion?
Yes, so I think there are some. I mean, it's more. It's motivated both from the small scale simulations and more from the observations where like we see these radio mode AGN in massive galaxies. And it's also partly because this way like we can correctly or efficiently quench the massive galaxies. Yeah, so it's both like a physically motivated thing and phenomenologically you need that to produce the correct scaling relation and the galaxy quenching. And so this is basically one of the scaling relation that we produce from all of these complex modeling. So as with a few other cosmological simulations, one of the things that you typically expect to see is first this the correlation between the galaxy mass and the black hole mass. And so this dashed contour and the dots are a few of the observation data points, and the central line and these scatter plots are is the simulation result. And another thing is the quenching on the massive end. So you see this is showing the star formation rate, and on the massive end we have a lower star formation tip, and this is plotted on top of the scaling relation. And so just to give you a broad sense, we are not the only cosmological simulation run to date. So this is like a previous work by Melanie Havley, which summarizes a lot of the recent state-of-the-art cosmological simulations and how different simulations predict about the relation between the stellar mass and the central black hole masses. And you can see that the simulations, I mean, with different models of stars and AGNs, the scaling relation can be different, and even with different resolution, it can be different. So there's still, I want to say there's still a long way to go for the simulations to really figure out the more detailed physics and to kind of reach some consensus on where things should lie. And another thing I want to point out is most simulation currently, including maybe our own, although I would argue we are a little better, is that they mostly produce a narrower correlation in this plane compared to the observation data set. So that might indicate we need more detailed physics to produce a larger variety of objects on this plane.
Could it be that just like scatter from the observations themselves would broaden these curves, or is that already included here? Are these like simulated mock observations within the simulation, or?
Yeah, that's a good point. You mean like the different like systematics that?
Yeah.
Yeah, I mean, that could also be the case. That's a good point. But I guess, I mean, for example, in this regime, it could be the case that there is some significant underestimate of the black hole mass from observations. But still, I think it's still like indicate a larger scatter, but that's a good point. We didn't like very carefully mock up the simulation prediction to exactly model what would be observed.
But also, sorry. You said in response to Odapan's question that one way that you decide what feedback prescription to use, that you want to be able to fit this. So your model is able to fit this. Presumably the people who are doing TNG 100 have chosen to tweak their model in order to fit something else. But what are you learning from? What are you trying to learn? I don't know.
So we don't aim to fit specifically. This is not a relation that we explicitly fit to in our simulation. The thing that if there's anything, the thing we fit is first of all the quenched the color distribution of galaxies compared to observations. So like it's this thing. And then it's the galaxy mass function and the AGN luminosity function. So the specific relation, we don't like do any tuning or fit.
Isn't the grand relation in somewhere or tuned to? This is related to, it, right?
Sorry.
Well, so I'd be surprised if anyone is conducting a simulation and they're not trying to fit them black hole mass velocity dispersion relation. But if they don't have black holes modeled, then I guess they don't.
We don't. I don't think like it's typical to tune this because I mean, at least I mean you could say that like intrinsically, if you have some Bondi accretion which accrete cold gas and you have a star formation model which kind of forms stars out of the same gas, then that's intrinsically like establishing this correlation. So that's true. I think in some sense we don't like fine tune this thing, but it's like a model that's more of a it's physically motivated and it has been yeah, so yeah, I don't think we specifically tune the parameter of the boundary accretion or the star formation efficiency to tune that, and or the feedback parameter. So the accretion model and the star formation model in, for example, in TNG and in Astrid are, you can say they are kind of the same, but they have different feedback mechanisms. So then they have kind of, different relations in this.
Another really naive question, could there just be an observational system at it where somehow there are actually like very massive black holes in low stellar mass galaxies that we're just not seeing them because they're faint or something like that? Like, you know, like where all these simulations are saying there should be things, we're just actually not seeing them for some reason.
Yeah, it's definitely possible. I mean, so this, oops. So if you look at the observation, in here, these are the AGN population, and also in the massive end is the elliptical galaxies. So it's true that for the lower end, there could be like things like if a black hole is not an AGN, then you do not see it. But you were saying like we have a very massive black hole in a small galaxy.
Mhm.
And we don't
I think it's different to not see and have
um
us bias in the maps.
it's
So, yeah, those are two different things that I was just wondering. For sure.
I think it's possible, but yeah, I would assume that if you have a more of a massive galaxy, then it would be easier to see them. But if it's not, either like dynamically or possibly through accretion. So I would say that the observation bias would more be biased the other way than what you said, but there could be possibilities. For example, I'll mention like a lot later where like if the black hole is somehow perturbed from the center, then it might be more difficult to see them. Oh, sorry, this is slow. Slide. Okay, and so like typically if you go to like a black hole simulation or modeling conference, this is roughly how people divide talks into groups and sessions. And so I already briefly mentioned the accretion feedback modeling in these simulations. So these are kind of the canonical thing that you should treat if you have a black hole in your simulation. But more often, there are other two aspects which are often more neglected or oversimplified, which is the dynamics of the black holes and the black hole seeding. So for example, in the dynamics, on the dynamics end, out of all these simulations, only Horizon and Astrid have a series dynamical treatment, and all the other simulation, they always pin the black hole at every galaxy center at each time step. So basically, during galaxy merger, like the black hole will always be where the minimum potential place, and then it will always be repositioned in there. So that's how like it's treated in these simulations. And in terms of seeding, most of the simulations prescribe a fixed seed mass above some certain halo mass threshold. And so in Astrid, we have more of a stochastic seeding based on the halo mass and the stellar mass. And in Horizon AGN, I think they have more of a gas-based seeding based on the gas density and metallicity. Today I'll focus more on the dynamics since it is like a very overlooked aspect. I would try to argue why it is important, why it also matters to these other things if you care about these other mechanisms. And I will talk about the consequences. So here I just want to mention that yeah, so they are divided usually into different days or sessions in the meeting, but they are really coupled. For example, if you care about the black hole accretion, but then the black hole moves around instead of always staying at the galaxy center, then the gas inflow might be significantly different. And you also have the binary accretion, which might change how the black hole accrete and how the orbit shrinks. And also if you have different seeding mechanism that might determine how the black hole behaves dynamically. And if you have a black hole that moves around, it can also, for example, have less of a feedback effect at the galaxy center, or it can have different shapes to the surrounding gas morphology. And so, yeah, as I mentioned, so these are the only two simulations that treat the black hole dynamics seriously in the simulations. And this is just a very quick illustration of what I mean when people reposition the black hole to the galaxy center. So you can see here, like there is a galaxy merger and more of a flyby encounter, and then in the reposition scenario, the two black holes are immediately stitched together. So in this case, this is like a real galaxy merger, so it might be slightly okay because the galaxies merge anyways. But there are cases where the galaxy doesn't merge immediately, but it's more of a radial flyby, and then one galaxy will steal the black hole from the other galaxy. So this can create serious problems.
So in a case like this, it's more a problem of defining when the merger happens. At least
So yeah, I mean, the obvious effect is
for the first
that
couple of orbits.
we delay the mergers. Yeah.
In the simulation where it's not pinned,
Mhm.
they look like they track the center of the galaxy still. So
I mean, the scale is still, I mean, eventually they will sync to the galaxy after like the years or will be a dynamical friction. So
what I'm saying is that if like it looks to me that in the simulation to the right, they still track the center of each galaxies after the merger. So right.
You mean the new galaxy or the old?
I could. What I'm saying is that if the prescription for when the galaxy merger happens is a bit later, then I don't know, they would look more similar.
You mean the black hole shrink to like the orbit shrink? Maybe I'll have another video later and then you can see more of a more prominent difference. But yeah, so this is like the main difference is the merging timescale, but here I want to mention like another reason why like you should care about this to model everything consistently. So for example, in TNG where they have reposition, one of the prediction is that after about redshift 1.5, all the black hole growth is significantly dominated by the merger. So this block curve is the mass accretion by merger, and then this is the accretion by gas. And so for all of these massive galaxies, they have significantly more mergers because of their reposition. And we actually calculated how much overestimation you can have if you have these kind of treatment. And so we predict that you will overestimate the mass accretion by merger by a factor of up to 5 if you have these early mergers. So basically, you stitch the black hole together, and then you merge things, but then you cannot, like you just merge things too quickly, and so you accrete too many of the black hole masses in this way. And then when you try to, for example, model the luminosity function and mass accretion by gas, maybe they have to tune their parameters so that they don't need as much gas. And so they have also tuned up their radiative efficiency. So these are all the consequences that can happen if you merge things too aggressively in the simulations. So here I want to just briefly introduce the dynamics of the massive black holes and different things that can affect them. So as I previously showed, we have galaxy mergers, and then after galaxies merge, It's usually the dynamical friction from either stars or dark matter or gas that can shrink the orbit down to scales down to like a few tens of parsec scales. And then on smaller scales, you would have other mechanisms such as the scattering with the stars, and also you might have multiple black holes in the center, so you can have like free body interactions, which might accelerate the black hole orbital shrinkage, or it might kick one black hole out. And then you will have the circumbinary gas disk, in which two black holes are embedded in the circumbinary disk, and then they can assist the orbital shrinking of the black hole. And then eventually you have the when the black holes harden, you will have the gravitational wave emission if all the other mechanisms are efficient. And then if you have gravitational wave, you might also expect a recoil kick depending on the mass or the spin alignment of the black holes. So among all of these mechanisms, the things that we can model in the simulation is only the first phase, or directly or resolve in the simulation is the first phase, which is the dynamical friction. So we can resolve the dynamical friction or the black hole orbit down to sub KPC scales in these simulations. And so the way we do it, for example, in Astrid, is we try to model both the dynamics from collisions particles and the friction from gas in these two different ways. And so we use, so the reason why we need to add a separate treatment for the dynamics, or we need to add these forces, is because of the limited mass and spatial resolution in the simulation. So essentially we need to compensate for the gravity that we're not resolving, which can play an important role in sinking the black holes. So on top of the gravitational force that already treated in the simulation, we have these separate forces which are tuned to the high resolution simulations to capture all the things that we cannot resolve at cosmological scales.
So, it is assumed that the distribution function is Maxwellian, or even for collisionless particles, which is not always a good assumption, especially in the centers of cusps, where the distribution function can be significantly non-Maxwellian.
Yes, so yeah, I agree. So I would say that, so the very inner cusp of the center, like the profile, we really cannot model very well anyways, like because of the softening in other particles. And so I think on the scales that so this is like a physically motivated model, but it's also, for example, you can see there's a balloon logarithm, which basically we understand that it's tricky to apply this to like a idealized treatment to simulations. So what we do is we also run simulations where we have higher resolution and we put black holes and let it sink, and we try to see what parameter goes into it, and you can recapture the orbit shrinkage of the black.
And you tune the ln lambda to high resolution simulation.
I would have thought your complaint would not be that the distribution function was Maxwellian, but that dynamical friction was completely differently when you're in a custom system.
Yeah,
The Maxwellianness is a side issue.
yeah. I mean, that is always the issue, but I don't know how to take that into account.
But there must be some regime in which this is okay, and in some regime in which it is. I don't know how you go from one to the other.
Well, especially if you have core galaxies, then you know that the Chandrasekhar dynamic friction doesn't work in the center.
So, you mean like all of the buoyancy thing that we see,
Yeah,
or
and
also like
solid.
some tidal effect that might. So, yeah, I agree, like we don't resolve all of these like for solving in our case, because intrinsically you can't really treat the interaction on that scales, but I think the hope is that with the larger scale tidal field, we already resolve it with the intrinsic gravity. So for example, any anisotropy in the galaxy on large scales, we can resolve it in the simulation. And so what we're trying to treat here is only on the scales in the immediate surrounding of the black hole. So like, it's not like we treat this on the galactic scale.
So the maximum scale in your log lambda should actually be that resolution
Yeah.
size, right? Okay.
Still have a question. Now you add by hand this force to the black hole in your simulation, but in reality, there's also feedback on the particles, right?
Yeah.
Is that any relevant?
Yeah, that's a good question. So in our model, we don't, another way to say, we don't conserve momentum strictly in this case. We don't add back reactions. In our simulation, I think in hindsight, we should have done it. But I think the effect should be small because last year, I think there's another group which tried to do this experiment. Like, so because there are ways of adding the damper friction which have some back reaction to the field particles. But then another group also compared different models of the damper friction, and they claim that the momentum effect to the surrounding particle on smaller scale is not very big. So some of the things we find after we include, oh, so by the way, anyway, so we're the first simulation which include both the damper friction forming gas and the collisionless particles. And so we also try to compare their effect for black holes at different evolution stages. So here, for example, is a direct comparison of the resolved gravity, the damper friction, and the gas. So this red line is the damper friction from stars and dark matter. The blue line is the friction from gas, and this is all compared to the resolved gravitational forces in the simulation. And we can see that and this is one example. This is all of the black holes in our test simulation. And we can see that in almost all the cases, the friction from stars is completely dominated over the gas force. But in some early phase of the black hole formation and sinking, the gas could still play an important role because in this high redshift regime, you could have more of these cold gas around the black hole compared to the star density.
The difference, sorry, to the
Oh, the top and bottom, or
yeah.
Oh yeah, so this is plotted as, so this is basically plotted as redshift. This is plotted as a function of the formation time of each. So here I subtract the seeding time of the black hole. And here is, so basically there's no strong redshift evolution, but it's more correlated with the black hole's age. And we also compare the black hole sinking timescale in the simulation to the prediction, which a lot of people use in semi-analytical models or in post-processing these repositioned black holes. The timescale at which the black holes sink to the center. And so this is for the massive, more of the massive systems. And here we incorporate this, the Chandrasekhar damper friction estimation, and this is a later model which kind of assumes that the secondary is embedded in some star system and then it gets stripped along the way. So we see that our simulations are consistent with these analytical predictions, but one thing I want to note is that there is a very wide scatter in the simulation. So it depends a lot on how the black hole orbit or the galaxy initial encounter happens, the galaxy morphology or the tidal interaction. So so if you want to have a faithful representation of how the black hole moves in the galaxies, it's still worthwhile to include these dynamical treatment in the simulations. And so I talk about the scales which we can comfortably resolve in cosmological simulation, but then there's all these other interactions on scales which cosmological simulations cannot really see. So if you want to model all these interactions, what can you do? So the first thing that people try to do is to create more like a kind of post-processing where like you take the mergers from simulations, you look at their surrounding galaxy properties and you try to extrapolate on these properties, and then you can estimate a time scale for each of these interactions. And you sum them up to do an estimation of the binary hardening time scale. And recently there has been a lot of, so this is okay, but this is still, there's too much of a stretch because you need to do too many extrapolations, and then if there is a significant delay, but you still merge the black hole in the simulation, you can then go into this early merger problem that I mentioned. And so people have been trying to come up with ways to understand this the small scale physics better and to connect the evolution at different scales. So there has been a group that tried to incorporate these models, but these post-processing models, but to kind of treat them on the fly, meaning that they don't merge the black hole until after this hardening timescale. And then you can also try to refine the dynamics around each of the black holes. So basically you create a region around the black hole where you want to resolve things better, and you treat the star interactions more carefully. And in our case, we try to take the original simulation and we try to use that to create initial conditions to create small scale and high resolution simulations to fully resolve the interactions on small scales. So I'll briefly talk about our work on that. So this is the general idea. So basically in cosmological simulation, we have a merger catalog, which are things that can shrink down to around KPC scales. And then we take the initial galaxy properties, we try to create, use the galaxy properties morphology and the orbital configuration to create idealized galaxy merger simulations. But then we can increase the mass resolution, we can increase the embodied treatment of the stars so that we can understand how the black hole really moves to the center or not in these cases. And so in our first suite of the simulation, we sample, this is the high redshift seed mergers in asteroid, and these points are the systems that we sample among the mergers as a test case. And so exactly how we achieve this. So for example, this is a really poorly resolved high redshift galaxy in asteroid. And then we see a merger here, and we then trace back to before the galaxy merger happens. So this is the original two galaxies and two black holes that are about to merge. And these are a few satellites around it, which will eventually also merge to the central region. And then we recreate these much higher resolution initial condition of these galaxy mergers and the gas like that. And then we forward run it. And so you see that in this case, the originally merged black hole would take a lot longer, and we can resolve a lot more orbit in this case. And the galaxy morphology and the structure is also resolved much finely. And this is an example of the resimulation profile of the recreated gas and stars and dark matter compared to the original simulation, and we resolve things down to about 100 or more times smaller scales, and we have a mass resolution that's 1,000 times better. I think I might skip this. So this is the a video showing this galaxy merger and the initial orbit in asteroid in orange, and then we recover this initial orbit, but then we can extend it to these scales.
Sorry, last question. When you do these simulations, do you have a way to also sort of try to embed the larger scale, like tidal field or like potential that this merger is in, like given the n-body structure that you have in this email?
Yeah, so we can do it, but so I think we tried to come up with to do it, but it's it's very hard and it's I think so it depends on also on the scales that we want to resimulate these things. And so I would say like for this first experiment is more of a we try to gain some understanding of on small scales what will determine like the small scale merger or not of these things. But I agree like the large scale things can be important. For example, out of a lot of the systems that we select, if you look at the large scale structure, because this is like high pressure 6 or so. So if you trace them forward a giga-year, a lot of things will fall in and it will be a completely different structure than it was. So I agree this is not like a very consistent way to remodel this. So then now the way we're trying to do this, we try to run individual Zoom simulations. We try to develop ways of like, I mean, it's already been developed, like we can run these multi-Zoom simulation. I think a speaker before also mentioned this. Like basically we can zoom into the systems and then we try to increase the resolution as large as possible, and then but also tracing the large scale environment. But this is more of a controlled experiment because as you'll see later, we also want to vary the inner density profile of these things to understand the merger timescale. But with Zoom simulations, it's hard to do that. Yeah, I think I'm running a bit late, but so this I already mentioned in the in the call lunch talk, so I will go through it quickly. So what do we learn from these three simulations? So one thing we learned is that so you see there's a large scatter in the dynamical timescale that was found compared to the analytical predictions. And the reason is that the first stage of the sinking, or like how large the black hole orbits start with, is very stochastic. So basically, if you look at these two comparisons, the large scale tidal field determines, or the galaxy merger initial stage largely determines the fate of the whether the black hole sink or stall in the first place. So this here I show the energy loss from the large scale gravity compared to the local dynamical friction, and in this case too. So you can see that for the systems that sink to the center more efficiently, there's this initial very rapid lose of energy in the first and second orbit of the galaxy merger. Whereas in the other case where the black hole stalls, some of the binaries can actually gain energy from the large scale tidal interaction. And so dynamical friction never really plays a role in this case. Whereas in this case, if the black holes sink to sufficiently small scales, then dynamical friction can play a bigger role in the energy loss. And so we found about 40% of the system in the resimulation can sink to small scales, whereas about 60% of them will stall in the larger orbits. And then, so this kind of naturally create a problem of the black hole not sinking in high redshift small galaxies. And so we also then try to experiment with what kind of galaxy environment might assist the sinking of the black holes. And basically we found that you need a star cluster around the mass of the black hole, or a little bigger than the mass of the black hole, to help the black hole to sink. And the reason why this sufficient sinking, it's not only that you have a larger mass to interact with the surrounding medium, but also because the tidal interaction between the two nuclear star clusters. So this leads to this rapid drop in the orbital size. And finally, this is
That drop seemed far too rapid. Is it?
sorry, this one?
Yeah, this one.
Yeah, this is basically you enter into the heart, the binary hardness. And this is kind of typical, like if you have two black holes, like it interact with dynamical friction, and then you will almost always see like a very rapid drop like the hardening of the binary is very fast. And then once it hardens, it can stall on that. So here we didn't show, but it can kind of, this is like the final parsec. So you can still spend a lot of time here until it emit gravitational waves.
Why is it happening so fast? Like it should happen in the orbital time? What is the orbital time? Seems. It's probably like wrong.
A mega year is the typical time scale for steeping around the friction, right?
Right.
You mean this drop is fast or like this is fast?
Means the drop, I think, but it's comparable to a dynamical time, is that right?
Yeah. And here, yeah, because also like you have the interaction between these star clusters, so you just immediately brings the, maybe like we don't have, we don't plot this thing very, we didn't zoom into this, so it appeared to be a very sharp drop.
This cluster assisted merger is happening once you get down to 10 parsecs or something, must be pretty small.
Yes, so this is 10 parsec because the scale of this thing is, I would say, parsec scale.
Yeah.
So like when it enter into like 10 parsec region, it starts to have some tidal interaction between the two clusters, and then after some point, it will immediately bring the black hole towards.
Is that a classic result? Or is that something newly discovered? Are these references like
Oh, sorry, so these references are the work that we've done, so like.
this year? It's very recent. I
If
tried this result before. If I take a point length and allow it to merge, it takes this long red time. And if I instead make it a fluffy thing that can strip, it merges much faster. It seems like a fundamental result.
Yeah, that Andres Escala was working on this in the early 2000s for his thesis.
Who's that?
Andres Escala, who's a grad student at Yale. Now
Yeah,
faculty.
maybe I should put more references here. I think in terms of the nuclear star cluster and how things sync faster, like through this tidal interaction. Another recent work, which I didn't put reference to here, is the work by Go Obia from Yale. I think he was postdoc at Yale, and then they also run simulations of like massive black hole binaries embedded in these clusters.
So by the two clusters coming in close to each other, they spring up some spirally kind of flinging off material, and that's where the angular momentum is going. That allows you to do that.
Yeah. Yeah, so this is basically. I don't have.
Thank you.
Okay.
5 minutes.
Okay, yeah, thanks for asking a lot of questions, but I should have rushed through some material. Yeah, so this is basically just taking the result that we have before and try to make a prediction of like how many mergers you would expect if you have different densities in the center, like different cluster environment. And basically if you don't have any high density material around the black hole, then it's very unlikely that we'll see any of these Irish mergers. Maybe I'll skip this sake of time. Yeah, this is basically showing some eccentricity evolution And some of the systems that merge very fast actually retain a very high eccentricity after partnering. And this is basically when the partnering happens. This is when the binary becomes bound binaries. And this is the eccentricity evolution. Okay, so this is next topic that I will try to talk about, but I don't have much time. Which is the off-center massive black holes and AGNs that we found in the simulation, and it also have a lot of observation consequences and current observations. So as you can see that because the black hole takes time to sink, and there's also other dynamical interactions such as three-body encounters or the recoil kits, the black hole does not always stay at the galaxy center. And so the observers can found these off-center AGNs, for example, by the line offset of the AGN with respect to the rest frame of the host galaxy. So there's like a velocity offset between the two, so it indicates that there might be an AGN that's moving. And you can also, for example, here is a work by Yue Shen, who tried to look for these off-center AGN by looking at the jittering of the center of like the jittering of light around the galaxy. And so they can constrain the maximum offset of these off-center AGNs as a function of redshift. This is an example of like an AGN here, and this is the host galaxy. And you don't find any other AGN in this galaxy. And there's also this work by Rins, which go and look at radio emission around the galaxy. So they look at compact radio sources, and they found that a significant fraction, about 10 to 30% cases, they see a compact radio source off-center from the dwarf galaxy. So this is the galaxy, and this red cross is where they find the compact radio sources. So this is very common in these dwarf galaxies. And in many of so in many of these cases, it only has the radio emission on the black hole's off-center, and so you cannot see it, for example, in the optical. And also, I think we also discussed this paper in the journal club. This is some very recent result where people found an off-center TBE in a massive galaxy, and they constrained the black hole mass to be around 10 to the 5. This is like very close to the center of this main galaxy. And there has been 3 off-center TDE found to date, and so all of them concentrate on this in this mass range. So all of them uniquely, all of them found a 10 to the 5 black hole within a 10 to the 11 galaxy. So these are the observation evidence. And in terms of how you can produce an off-center AGN, these are some of the main mechanisms. The first, you can have the very typical black hole saving time spectrum merger. So for example, this is like a massive black hole stalling case. So this is a merger between 2 10 to the 7 black holes, and one of them immediately grow by eating all the gas in the surrounding medium, and the other just remains inactive and off-center for a very long time. And in addition to these like major mergers, you can also have a black hole that's initially sitting at the center of a BCG, but then because of infalling satellite, here this is a work by Eileen Chu, and basically they follow the initially central BCG, and this is like a kick by the so they trace in simulation the infalling orbit of all the satellites, and then they calculate how much the central black hole will be kicked or perturbed from the center each time there's a satellite on a radio orbit, and this is basically this one is kicked 3 times over this. time period. And then finally, this is the other cases where you can probably gain a larger velocity kick and to perturb the black hole to a bigger radius. So you can have a three-body interaction. So this is a paper by Partman recently, which they try to model the merger of a lot of black holes in the satellite galaxies. And here is the orbit of all these black holes, and this is a three-body interaction. So the empty triangle are three-body interaction kicks, and then this black triangle is a recoil kick. So in this case, even though the black will sink initially, it will constantly be perturbed and kicked from the center. Yeah, so in the following, I will talk about the population of wandering black holes. I want to remind you that within the current scope of simulation, we only have these two protection mechanisms. So we're still working on incorporating the recoil kick and three-body interaction to the simulation to produce the full population of these wandering black holes. And so this is like earlier when I played that video, you think there's not a lot of difference between the two, but then I would say that if you have like the dynamics treated properly, you would have all these wide orbit things, especially in these massive galaxies. So otherwise, like if you look at, for example, TNG, you probably only see one thing in the center, and then maybe some black holes in the bigger satellite, but not all of these things. And this is the population of wandering black holes that you would see in these very massive galaxies. And so we then quantify the fraction of them compared to the central galaxies and the mass fractions. So for example, this black curve is the total black hole mass function in the simulation. And then, sorry, here we didn't extend to bigger scales because in this work, we care about like these C wandering black holes. And and the blue curve is the central black holes. So you can see that in this mass regime, basically in the seed regime, most of the seeds are already found in these massive clusters as wandering. So only a smaller fraction of the black hole seeds are in isolated galaxies on its own and still not stripped of the host. And then on the massive end, however, we still see a significant fraction of these wandering black holes and off-center black holes. For example, if you go to 10 to the 8 solar masses, we still found about 10% of the black holes that are wandering, and then about 5% or so of these black holes are off-center in the subhalos. And so if these black holes are wandering and they have composed of a significant fraction, we might want to understand if we have a chance to see them or not, or whether they can explain some of the hyperluminous X-ray sources. And so here we quantify the total number of these wandering black holes in massive galaxies and what fraction of them is bright in the X-rays. So basically the black hole is bright in X-rays only if they encounter some parcel of dense or cold gas, or if it's a disk galaxy, it then orbit across the disk, then it can shine bright for a very small amount of time. And so, yeah, we can have hundreds of these wandering black holes, but only about 1% of them can be seen as bright X-ray sources. And this is the overall number density of the off-center black holes we see in the simulation. And so this is kind of expected and consistent with the current observation result that you see 3 of these off-center black holes and all of them are in 10 to the 11 galaxies. So this is a consequence of convolving the galaxy mass function basically with the increased number density of black holes, then you naturally get a peak at the 10 to the 11 galaxies. I think I'm out of time probably. So I would just finally mention that we found about 10 to 20% of massive galaxies do not host a central massive black hole. And these are galaxies characterized by high star formation rate because there's no efficient AGN feedback because there's no central black hole. And in these cases, it's still likely that we see the black hole that is off-center if it's luminous around here. But there's also a significant amount of these off-center big black holes that is not bright and we might not be able to see them. Yeah, this is just some gallery of images because I want to understand what the host galaxy and the black hole look like. So I produced these images just for myself to see, but I think it's very interesting to just see the diversity of morphology of these off-center black holes. Because initially I would expect to see a lot of tidal features around each, but you see these very weird shapes, these tidal interaction indicating of a recent merger. But there's also cases where the galaxy appears more in equilibrium and giant. And this is still in progress, but I think it's good to see the images. Thanks. I will conclude my talk.
And if you have any questions, maybe there's time for one last question.
Yes.
The isolated cases where the galaxy is nearly in equilibrium, have you checked the density profile of the halo? If it is cuspy or core, then maybe there is core strong.
Yeah, I checked the density profile of the stars. It does appear to have a plateau somewhere like on a few kpc scales. So but it's not. It's interesting because I feel like the flattening happens on even larger scales than the typical core of these type of like the typical core you expect in, for example, elliptical galaxies. And some of these are actually a bit disky. I haven't done like a full decomposition of the star into disk and bulges, but I think they're not exactly the same as a typical core elliptical. Like the core that you would expect. It's like there's a flattening on larger scale, which is a bit curious, and I'm still trying to see like why it forms, how that happens. So, and you also said some mechanism that can.
Yeah, I was just wondering that if the galaxy has a core, either in the halo or in the stars, then core stalling might be offered.
Yeah.
The
Yeah, I think
isolated
that's
cases
definitely a
might have.
possibility, yeah.
Okay. Can continue our lunch if there are more questions. Thank you.